Have you ever wondered what powers the most destructive force on Earth? It's not magic, but science, a force that dwells within the heart of atoms. The power to both illuminate our world and potentially destroy it. Today we journey into the atom, to the realm of nuclear reactions. We'll explore the processes that fuel stars and unleash unimaginable energy. We'll uncover the secrets of nuclear fission, the splitting of atoms, and nuclear fusion, the merging of atoms. But be warned, this knowledge comes with a heavy price. We'll also delve into the terrifying truth behind atomic bombs, the weapons that harness the power of the atom for destruction. Are you ready to unlock the secrets of nuclear power? Imagine a force so powerful, so fundamental, that it could fuel stars and level cities. That force lies within the heart of the atom, in the process we call nuclear fission. Picture an atom like uranium, a giant in the atomic world. Inside its core, the nucleus lies a cluster of protons and neutrons bound together by the strong nuclear force. But what happens when we disrupt this balance? Introduce a neutron, and the consequences are dramatic. The nucleus, now unstable, begins to vibrate violently, splitting into smaller atoms, often barium and krypton. This splitting releases energy, as described by Einstein's famous equation, E=mc². Even a tiny bit of mass translates into a tremendous amount of energy. This energy, released as heat and light, drives nuclear power plants. By harnessing the fission of uranium atoms, we generate heat to boil water, create steam, and spin turbines that generate electricity. But fission is a double-edged sword. The same energy that powers our homes can also fuel the most destructive weapons ever created. This uncontrolled chain reaction is the heart of an atomic bomb. If nuclear fission is the process of splitting atoms, then nuclear fusion is its polar opposite, a cosmic dance of creation. It's the process that powers the stars, including our sun, and holds the key to potentially limitless clean energy. Imagine the immense heat and pressure found at the heart of a star. Temperatures so extreme that atoms are stripped of their electrons, forming a sea of plasma. Here, fusion occurs. Hydrogen, the lightest element, takes center stage. Two hydrogen nuclei collide with unimaginable force, forming a single nucleus of deuterium. This deuterium nucleus then collides with another proton, creating a helium-3 nucleus. Finally, two helium-3 nuclei collide, forming a stable helium-4 nucleus. With each step, energy is released, radiating outward from the star's core. Fusion produces no long-lived radioactive waste. Its fuel, hydrogen, is abundant, found in seawater. It's the ultimate clean energy source, a promise of a future free from fossil fuels. Yet, achieving fusion on Earth is a monumental challenge. The power of the atom is a double-edged sword. In the hands of scientists, it holds the promise of clean energy and medical breakthroughs. But in the wrong hands, it can be twisted into a weapon of unimaginable destruction. The atomic bomb stands as a stark reminder of this duality. At its core, the atomic bomb is a device designed to unleash the raw power of uncontrolled nuclear fission. It takes the chain reaction and pushes it to the extreme, creating an explosion that can vaporize cities. Imagine a sphere of highly enriched uranium or plutonium surrounded by conventional explosives. When the explosives detonate, they compress the uranium or plutonium, initiating an uncontrolled chain reaction. Neutrons bombard the nuclei of surrounding atoms, releasing more neutrons in a runaway chain reaction. The result is a blinding flash of light, a searing wave of heat, and a shock wave that levels everything in its path. Fusion in hydrogen bombs, the thermonuclear nightmare. The hydrogen bomb, a weapon 1,000 times more powerful than the atomic bomb, harnesses the power of nuclear fusion. Fusion bombs utilize the energy released when light atoms, such as isotopes of hydrogen, are fused together. The key to unlocking the H-bomb's power lies in a two-stage process. The first stage, the trigger, is a fission bomb. This fission explosion creates the extreme temperatures and pressures needed to ignite the second stage, the fusion reaction. When the fission bomb detonates, it unleashes a torrent of X-rays and gamma rays that bathe the fusion fuel capsule. This intense radiation vaporizes the capsule and heats the lithium deuteride to tens of millions of degrees Celsius. Under these conditions, the lithium deuteride undergoes fusion, releasing a staggering amount of energy. The result is a thermonuclear inferno, a fireball that vaporizes everything in its path. Fission versus fusion, key differences, splitting versus merging. Fission and fusion, two sides of the same atomic coin, both capable of unleashing unimaginable energy. Fission is the process of splitting heavy atoms like uranium or plutonium into lighter elements. This splitting releases a tremendous amount of energy, as a portion of the atom's mass is converted directly into energy. Fusion is the process of combining light atoms, such as isotopes of hydrogen, to form heavier elements like helium. This fusion process releases even greater energy than fission. Fission relies on heavy elements like uranium and plutonium, which are relatively rare and carry significant environmental risks. Fusion utilizes hydrogen, the most abundant element in the universe, as its fuel. Fission produces radioactive byproducts with long half-lives, posing significant challenges for long-term storage and disposal. Fusion produces far less radioactive waste. The challenges of controlling and harnessing these reactions also differ significantly. Fission reactions can be initiated and controlled with relative ease. Fusion requires incredibly high temperatures and pressures, conditions that are exceptionally challenging to create and maintain. Nuclear energy, power or peril, a choice for humanity. The atom holds within it a power both awe-inspiring and terrifying. We've witnessed its destructive potential in atomic bombs and nuclear meltdowns, yet we've also glimpsed its promise, its ability to power our cities. Nuclear energy stands at a crossroads, a testament to human ingenuity and a reminder of our capacity for both creation and destruction. The question is how we choose to wield it. Nuclear fission offers a carbon-free source of energy, a powerful tool in the fight against climate change. However, the risks associated with nuclear power are undeniable, the potential for meltdowns and the challenges of radioactive waste disposal. Fusion power offers a future free from these risks. Fueled by abundant hydrogen isotopes, fusion reactions produce no long-lived radioactive waste. Yet the path to fusion power is fraught with challenges. The future of nuclear energy hinges on technological advancements, political will, and public perception. The choices we make today will determine whether the atom becomes a force for good or a harbinger of our demise. As we stand at the precipice of a new era, grappling with the challenges of climate change and the ever-growing demand for energy, the atom continues to beckon. The choices we make in the coming years will determine whether this powerful force becomes our salvation or our demise. Will we harness the atom's power for good, developing safer and more sustainable nuclear technologies? Will fusion power, the dream of clean and limitless energy, finally be realized? Or will we succumb to fear and short-sightedness, turning our backs on a technology that could hold the key to our future? The future of nuclear power, and indeed the future of our planet, rests in our hands. Let us choose wisely. Like, share, and subscribe for more mind-blowing science stories.